using matrix algebra techniques to find a general solution to the system. So first we will turn this system of equation into the matrix form. So we have x prime, y prime, put that in the matrix, 2, -5, 5, and -24 times xy. And we can write that as a matrix form times A x, where the matrix A is equal to 2, -5, 5, and -24. We're going to find the eigenvalues and the eigenvectors for matrix A, and from that we will write the solution. First, the eigenvalues. Which is the determinant of A minus lambda I equal to 0. So pretty much we have the matrix A minus lambda on the diagonal equal to 0. Notice this is a scalar equation, not a vector equation. So that's just a number 0, not a vector 0. Alright, determinant of a 2 by 2 matrix. All we need to do is just multiply in this direction minus the other direction. So we have 2 minus lambda minus 24 minus lambda minus -25, that is plus 25, equal to 0. Multiply them out, -48 minus 2 lambda plus 24 lambda, so that would be plus 22 lambda plus lambda square plus 25 equal to 0. So we have the equation lambda square plus 22 lambda minus 23 equal to 0. If we factor out, we will have lambda minus 23 and lambda plus 23 and lambda minus 1 equal to 0. So we have two eigenvalues, lambda equal to 1 and lambda equal to -23. Lambda 1 is 1, lambda 2 -23. So we have two eigenvalues. Now we find the eigenvectors for those eigenvalues. Just switch to color here. For the eigenvalues of 1, we will solve the equation in this form of A minus lambda I times the vector V equal to 0 vector. So we have the matrix A, 2, -5, and 5, and -24. We will subtract the eigenvalues on the diagonal. And then we multiply V1, V2 equal to 0, 0. Right? So we write the matrix form of 1, -5, and 5, -25. Obviously, we see second row is negative 5 times the first row, so the elimination is easily done. But I just use the calculator here because later on when we have 3 by 3, it will be easier if we know how to do that on a calculator. Right, and I do 2 different ways too. If we use TI-84, then we just do this directly and enter the matrix, alpha, zoom, everything on the home screen. If we use TI-83, we have to store the matrix separately. Anyway, 1, next, negative 5, 0, 5, negative 25. We can do this by hand easily, but I just want to get familiar with the calculator. So we can write like that. Only the top equation has some meaning to it. So 1v1 minus 5v2 equal to 0. So we can say v1 is 5v2. So from that we can write the solution as v1, v2. v1 is 5v2. v2 is still v2. Factor out the v2. We have 5 and 1. That is the eigenvector. We say eigenvector 1 is 5 and 1. Right. Now we do the same thing for the second eigenvalues of negative 23. We have the matrix 2, negative 5, 5, and negative 24. We will subtract the eigenvalues. In this case, minus negative 23 is plus 23 on the diagonal. Sorry, on the sudden I changed the color to blue for no reason. Again, we just keep the equation in that black ink. Anyway, so we have 25, negative 5, and then 5, and negative 1. Again, we should see one row is a multiple of the other row only when we have 2 by 2 though. If we have 3 by 3, that might not be the case. So because this one 2 by 2, the first row is negative 5 times the second row. Anyway, we do reduce row echelon form here also. And I'm using the TI-83 form. So we store the matrix, second matrix, and now we'll go to edit. Let's put that into the matrix B. So go down and hit enter. It is a 2 by 3. We have 25, negative 5, 0, 5, negative 1. Right? And then second mode. Go back to the matrix again and do the reduced row echelon form. This time we apply to the matrix B. So given the names, go down to B. And then we have that. We can convert to fraction if we want to. So we have 1, negative 1/5, 0, 0, times v1, v2 equal 0, 0. Again, only the first equation has some meaning to it. So we say V1 is 1/5 V2. And we can write the solution as V1 V2 equal to 1/5 V2 V2. Factor out V2, we have 1/5 and 1. Right. Even though that works just fine, but usually, again, eigenvectors, it's not just one vector, it is the whole space. So pretty much we can choose any V2, we choose any number for V2. Notice that if we pick V2 to be 5, then that turned out to be something a lot similar. So what I usually do in this case, when we have the fraction, just multiply by 5. In that case, we have 1 and 5. And we don't have to deal with fraction. Right. So we have 2 eigenvalues and 2 eigenvectors. Now we just write the solution. The solution will be in the form of C1 E lambda 1 T eigenvector V1 C2 E lambda 2 T eigenvector 2, which is C1 E to lambda 1 is 1 times the vector V1 5 and 1 plus C2 E2 eigenvectors of negative 23T, and then eigenvector is 1 and 5. We can leave the answer in that vector form, or we can, if we multiply it out and combine them. So we multiply C1 e to the t on the top. We have 5 C1 e to the t on the top, and C1 e to the t at the bottom, plus C2 e to negative 23t on the top, and 5 C2 e negative 23t at the bottom. And when we add these vectors or this matrix, we should have 5 C1 e to the t plus C2 e to negative 23t and C1 e to the t plus 5 C2 e to negative 23t. And you see, when we write like that, this look like what we have earlier when we have the system of equation. But we can leave the answer in any form. But I usually keep in this vector form or just multiply it all out. Let me zoom out to have the whole problem. So pretty much we turn the system of equation into the matrix form. We find the matrix, the square matrix A, find the eigenvalues and eigenvectors. Once we have the eigenvalues and eigenvectors, the solution given in this form, the linear combination of C times the linear combination of E to lambda T plus, I should say, linear combination of E lambda T times the vector, eigenvector. And that's all we have.